Flat earthers contend that the atmosphere magnifies things in the distance in such a way that they get too large and the bottoms go beneath the horizon and get hidden. Let's have a look at what really makes things in the distance sometimes appear different sizes in relation to each other. It's called perspective. Flat Earth proponents, like Rob Skiba, will offer images such as this and say, look at how large the Willis Tower looks in relation to the boat, and how small it looks in relation to the car. That must mean that the atmosphere is magnifying the Willis Tower in the second photo, because the camera now has to look through miles and miles of atmosphere. But they never offer any real measurements or calculations. Earlier this year, I had a Flat Earth proponent on Twitter try to tell me the molecules of water in the atmosphere are causing the more distant objects to be magnified more than those close up, and that is why they appear larger, and also why their bottoms slip below the horizon. So I set up a little demonstration in my backyard to explain the mathematical relationships between relative sizes. Here, I demonstrate that if I have two balls, where one has a diameter 10 times greater than the other, they will look the same size in my video if the larger ball is also 10 times further from my camera. I'm able to position my camera so that the little ball perfectly eclipses the larger one. Please excuse my breathy nature in this video. Much like I am today, I was sporting a cold at the time. Let's watch.
Oh, I'm going to try and make you understand what perspective is all about. It's completely mathematical. Now, you'll notice I have a couple of balls out here, a rather large beach ball and a much, much smaller bouncy ball. Now, I measured their diameters. The diameter of the beach ball up here is approximately 30 inches. I'll do this in inches so that you don't have to worry about converting from metric. And I have put it right here at the 20-foot mark on my tape measure. Okay. So that beach ball has its center basically on the 20-foot mark. Now this other little ball down here has a diameter of approximately 3 inches. So it is 1/10 the diameter of my rather large beach ball. So I have put it here 1/10 of the way along at 2 feet. So it's at my 2-foot mark. Now I'm going to go down to the 0 and you're going to see it look exactly the same size as the little ball eclipses the beach ball. And you'll see I'm right, if I turn down, I'm at the 0 here, excuse me, and we've got an eclipse of the beach ball. Move to the side, they look the same size, basically not quite the same shape because it's a beach ball. And I'm moving my camera around a little bit. That's mathematics, not molecules. I'm going to try to demonstrate something else about perspective here. We're going to start with our eclipsed beach ball. So I'm at the 0 mark on the tape measure, and I'm going to pull the camera back. Now what you're going to see is the pink ball reduce in size quite rapidly, and the beach ball in the background not so much. And I'm going to pull the camera back about 2 feet, so I'm about twice as far away from the pink ball as I was before. So I'm going to pull it back. Right here is about 2 feet back from the beginning of my tape measure. And you can see that the ball is about half the size of the beach ball now, instead of being the same size. I'll just move it up and down so you can see that a little bit in the parallax. Now, the reason this happened is because I barely moved away from the beach ball. So it hardly changed size at all. It was 20 feet away, it's now 22 feet away. Where the little pink ball, I was 2 feet away and I doubled my distance. I'm now 4 feet away. So I doubled that distance, but I barely changed the distance I was away from the beach ball. It's all relative distances. It's all math, not molecules.
So here's what happened. First, note that in my real-life demonstration I used a scale factor of 10. Here I'm using 5 so that it fits nicely in my screen. So here, 3 units away from my eye, I'm going to place a ball that has 1 unit, up here 1 centimeter, 1 unit of diameter. So we'll put it right there. Maybe adjust it just a titch there, so that it's within the angular line of sight. Now if I take a much larger ball and place it 5 times further away, here at the 15 units, it stays within the lines defined by my angular line of sight. So let's take my ball tool again. This time I'm going to make it 5 times larger, and we're going to place it 5 times further away up here at the 15 unit mark. So put it there, and I put that a little bit high. Let's pull it down there. It stays within my angular line of sight. It appears to have shrunk to the size of the much smaller ball. In other words, by moving it 5 times further away, it appears to have decreased to 1/5 of its size. Now we can analyze this mathematically using similar triangles. The diameter here of the much larger ball is 1 side of this big triangle, and the diameter of this small ball is 1 side of this small triangle. Each triangle has the same measures of angles. It's got this angle in common, and these 2 smaller angles are exactly the same because these 2 lines are parallel to each other. What this means is that one triangle, the blue triangle, is just an enlarged version of the other. All the side lengths of the large triangle are just 5 times that of the smaller triangle. It's a purely mathematical relationship based on the straight line of sight to the edges of the balls. Simply mathematics. Now flat earthers will say, but that's just your backyard. You aren't looking through miles and miles of atmosphere. That's not the same as looking across a lake at what's on the other side. Now earlier in the summer, my family and I went to Hamilton, Ontario to tour some waterfalls in the area. Very pretty, I highly recommend it. While there, we were blessed with a day that was clear enough to make out the skyline of Toronto in the distance. Equally lucky, it was also a day where both the surface temperature of the lake and the air were at about 25 Celsius, so there wasn't any apparent refraction. I managed to convince my husband to drive to 2 separate locations to view Toronto. My goal was to compare the amount missing off the bottom of the CN Tower from 2 different elevations to globe predictions. I will show the results of that in a separate video. These 2 locations also happen to be 2 different distances apart, 53 kilometers and 59 kilometers approximately. If perspective follows the same rules through these great distances in moisture-laden air, see the fog, as it does in my backyard, the CN Tower should appear approximately 58.7 divided by 52.7 or 1.11 times larger in the closer picture. If the atmosphere does indeed magnify things, I shouldn't find this relationship at all. Perhaps the more distant photo will be the same size or even larger than the closer picture. Now these 2 photographs were resized when I cropped them together to make the CN Tower the same height. So I'm going to need to go back to the original unedited photos in order to compare the size of the CN Tower in each image. Let's see what I found. First thing I'm going to do is pull in these pictures of the Toronto skyline that I took. These are unedited pictures. They are straight off of my P900 camera. They were taken at maximum optical zoom, which is 83 times optical zoom. Now you can see it's pretty foggy here. This is the picture where I'm further away. I've taken it at the top of the escarpment. This one's not quite as bad. You can see it a little bit better because I am closer. I'm about 10% closer in this photograph than I was when I took this one up here. We're going to make it so that I can see the CN Tower just a little bit better. So I'm going to go into, oops, my mouse doesn't want to behave here. We're going to go to Adjust, Shadows and Highlights. And you can see that's already a little bit better, but I'm going to pull up the highlights a tiny bit so I can see it. And now I'm going to go and do the same thing to the other photograph. Image, Adjust, Shadows and Highlights, and pull up the highlights there so I can see it. Now I'm going to take some measurements of the circular part here of the CN Tower. My pictures aren't from exactly the same angle. You can sort of see here that there's more area around the CN Tower in this picture than there is in this one, or there's a bigger gap over here. My two pictures weren't exactly in a line, so the other buildings are going to be affected by that little bit of a parallax shift, where the top of the CN Tower is round, so it shouldn't be affected that much. So I'm going to go in and we're going to use the ruler tool on Photoshop, which is right here. And I'm going to take three measurements here. I'm going to measure across the bottom here of this white part. If you've been at the CN Tower, this is the glass floor layer. So I'm going to measure from one side to the other, right about like that. And we'll look up here and it tells me that that is about 1.73. Now I'm going to put that in here, 1.73. That is in centimeters. And we're going to figure out what I have here in the spreadsheet. This is going to divide these two terms when I get it to see what that ratio is. Remember, we're looking for it to be somewhere around 1.1. So I'll take two more measurements. I'm going to measure this part in here across the narrow band of the CN Tower. So we'll go from here to here. And I'm taking three different measurements because it's kind of hard in these photographs to actually see exactly where we are. So the more measurements we compare, the better. I could get a measurement error in one of them. So this one, it looks like 1.52. So we'll go and we'll put that in here, 1.52. Now the last one, so that I get it in the other direction as well, I'm going to measure from the bottom of the glass floor layer up here to the sky pod. So we're going to measure from here, right about there. We'll go up so that we get a vertical measurement as well, up to the bottom of the sky pod. So that looks like it is about 4.67. So 4.67. Now we're going to go and make the exact same three measurements in the more distant photograph and see how close we come to getting a 1.1 measure. Okay, so this looks right about here. It's a little hard to see. This is why we're taking three different measurements from there to there. And what does that tell us it is? It looks like about 1.5. So that's our first measurement. 1.5. Oh, look, we've got 1.1 there already. We'll round to 1.2, but 1.15 is pretty darn close. Let's take the second measurement. We're going to measure from here over to here. This one's kind of hard to get on here. I'm going to try that again. Let's clear that off. I think it's right about there. This might be the least accurate one, trying to get where it is. So that looks like it's about 1.25. So 1.25. I'm starting to lose my voice here. Ooh, 1.216. Yeah, that one, not getting it. That one's really hard to get. Let's try the last one. So we're measuring from the bottom here up to the sky pod. So I want to go from about here up to about here on the sky pod. I think it's about where I had it before. There. And that tells me it is 4.17. So we go over here to 4.17 and 1.1. Okay, so this one's a little off, but it was a little tricky trying to get that measurement, but it looks like it's about 1.1. So from this, the relationship through these miles and miles of moisture-laden fog has exactly the same relationship as the balls in my backyard did. So it doesn't appear that the atmosphere is doing anything to change the relationship of the size. I don't see anything that says that going further away magnifies what we're looking at. There's just nothing.